Numerical operations can be performed on every element in a vector or a matrix. For example, scalar multiplication means taking every element and multiplying it by a scalar. For example, here's a vector that has 3 elements, 4, 0, 11, and we're going to take each element in the vector and multiply it by 3. So 4 times 3 gives us 12, 0 times 3 gives us 0, 11 times 3 gives us 33. Another example, scalar addition, add a scalar to every element. So for example, zeros, 1, 3 gives us a 1 by 3 vector of all zeros, add 5 to each gives us a vector of 3 5s. So these are in general called scalar operations. Array operations are operations on two matrices A and B. What happens is that the operation is applied term by term or element by element, which means that the matrices must have the same dimensions to begin with. In MATLAB, to do matrix addition, for example, if we had two matrices A and B and they have the same dimensions, we could just say A plus B, and that's automatically going to go through every element in A and add the corresponding element in B to it. Matrix subtraction, same thing. We could just say A minus B or B minus A. However, for operations that are based on multiplication, which means multiplication, both division operators, and exponentiation, a dot must be placed in front of the operator. So for example, array multiplication means multiplying term by term or element by element. A dot star or dot asterisk B is how we would do that. Array division, A dot slash B, either one of the division operators. And array exponentiation, for example, take an array and square it, A dot, and then the little caret symbol 2. So again, the array multiplication means the matrices have the same dimensions. We're just going through element by element and multiplying the corresponding elements. So that's not the same as matrix multiplication. This is what is called array multiplication. So matrix multiplication is a completely different thing, and it's a little complicated. So first, we're just going to talk about the dimensions. So matrix multiplication is not an array operation. The matrices are probably not going to be the same dimensions, and this does not mean multiplying term by term. In MATLAB, just the asterisk is the multiplication operator that performs this matrix multiplication. So there's a very specific definition for matrix multiplication. Let's talk first about what the dimensions of the matrices have to be in order to be able to multiply them. So if you want to be able to multiply a matrix A by a matrix B, the number of columns of A has to be the same as the number of rows of B. So if the matrix A has dimensions m by n, that means that matrix B must have dimensions n by something, whatever. We'll call it P. So in mathematical notation, if the matrix A has dimensions m by n, then matrix B has to be dimensions n by P. And what we say is that the inner dimensions must be the same. So let's repeat this. If A has dimensions m by n, so I'm going to write that in here, A is m by n, then matrix B has to be n by something. We'll call it P. So again, we say that the inner dimensions agree. So the number of columns of A and the number of rows of B. So that's what you have to have for the dimensions in order to be able to multiply these together. Now the resulting matrix C, so when we do that, we're going to get another matrix, let's call it C, that has the number of rows of A, which is M, and the number of columns of B, which is P. So again, if A is m by n, then B has to be n by something. So we say that the inner dimensions here have to agree in order to be able to perform this multiplication. And then the resulting matrix is going to have the outer dimensions m by P. So far we haven't said anything really about how you multiply matrices together. We're just talking about what the dimensions have to be. So here's how you find the actual elements of the resulting matrix C. It's the sum of products of corresponding elements in the rows of A and the columns of B. So for each element in C, C sub ij, it's the sum of rows in A and columns in B. So what you're doing is multiplying those corresponding elements and adding them all together. So here's an example. So if we call this matrix A and this matrix B, the resulting matrix is going to be C. A is 2 by 3, B is 3 by 4. So the inner dimensions agree. That means we can perform this multiplication, and the result will be the outer dimensions 2 by 4. So notice this is 2 by 4. Okay, so how do we come up with every individual element? Let's start with C sub 1, 1. We find C sub 1, 1 by using the first row of A and the first column of B. So notice they have the same number of elements, the rows of A and the columns of B, so we can multiply term by term and add them all together. So in other words, this C sub 1, 1 is 3 times 1 plus 8 times 4 plus 0 times 0 gives us 35 as a result, as written down here. So let's just pick another arbitrary one. A sub 2, 2, or rather C sub 2, 2 is going to be found as the second row of A and the second row of B. Again, multiplying terms, 1 times 2 plus 2 times 5 plus 5 times 2 gives us 22 as a result. So all of the values in the first row of C are going to be found by using the first row of A and in sequence the 4 different columns of B. And then the second row in C is going to be found using the second row of A and in sequence the 4 different columns of B. So pause this for a few minutes, take a few random elements in C and make sure that you understand how we arrived at these numbers. Now, since vectors are just special cases of matrices, the matrix operations that we've described, including addition, subtraction, scalar multiplication, multiplication, and transpose, they work on vectors as well, as long as the dimensions are correct. We also have specific vector operations. The dot product, or the inner product of two vectors, A and B, is defined as A1 times B1 plus A2 times B2 plus A3 times B3, etc. And there's a built-in function dot to do this. Also, if you're taking a mechanics class and you know what a cross product is, there's a built-in cross to do that.